and Professor Jawar Singh from IIT Patna. So, on behalf of Punjab Engineering College, let me welcome Dr. Jawar Singh from IIT Patna. He is working as an associate professor in the Department of Electrical Engineering. Dr. Jawar Singh received his PhD degree from Department of Computer Science and Engineering, University of Bristol, UK in 2010. He has been associated with Triple IT Jabalpur, and since 2017 he is with IIT Patna. His research interest includes low power devices and circuits, RF energy harvesting, etc. Dr. Singh holds two US patents related to static RAM, random access memories, and he has received prestigious Indo-US Fellowship Bhavan 2016. He has authored more than 100 papers in journals as well as in conferences and a few book chapters in from the publishers like Springer, etc. He has been involved in various research projects funded by DST, MIT, and total amount is more than 10 million INR. He has also been the visiting researcher at Pennsylvania State University, USA in 2009 and at University of North Texas in 2016. He has also received many prestigious recognitions, awards like Senior IEEE Membership Grade. He has received Best Paper Award in 2015. He has received Inventor Incentive Award from Pennsylvania State University. He received Worldwide University Network Fellowship UK in 2009. He received National Overseas Fellowship in 2005. So with this short introduction of Professor Jawar Singh, I request him to deliver his talk on semiconductor devices and circuits for brain-inspired computing. So over to you, sir.
Thank you, sir. Thank you very much for a detailed introduction. I should have forwarded a brief biography actually.
No, that's
Okay.
fine.
So, so thank you very much once again for inviting me for this short-term course, and to you and your team and Punjab Engineering College, Chandigarh. And so let me get started with this today's talk. Title is Semiconductor Devices and Circuits for Brain-Inspired Computing. So in this talk, what I'm going to deliver or talk about are as follows. So first of all, uh, I will start with the outlines. Sir, if there is any interruption or any problem, you just please call me or even interrupt me also. And I'm assuming
Sure,
that
sir.
quality of audio, video, everything is perfectly fine, right? So just please.
Yes, 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 sir.
All right. So the outline of my talk, today's talk is we will start with the motivation, alternative computing approaches. Why do we need these alternative computing approaches? An important aspect basically. If you see, there are variety of computing approach are popping up, coming up, and for that definitely we need some devices and circuits they can perform these computations, because it is not just only the software that matters, but it is a hardware that is equally matters. And then so I will talk about two specific computing approaches. One is the neuromorphic computing, that is also called the computing inspired by human brain, and as an alternative it is also a in-memory computing, and they share common things basically. So that's why I put basically both these computing approaches together, because there are certain parameters and certain things are quite common. Then I will talk about the elements, they are like the devices and circuits or the models that are required for performing these computations, and some of the applications research perspective, and that we will summarize the talk. All right. So let's before moving to this, let's set the stage why we need some alternative computing approaches. And for that, I'm just showing you with this picture. See if I can get rid of this camera.
So there is one window open right side. Yeah, now it is okay.
Yeah, this is what I was trying to do actually. All right.
Okay.
Yeah. Okay. So the motivation to set the stage of this talk. So from this uh, picture, we can see that here I have shown the uh, clock frequency or the clock, just a minute, on this axis, and here is the power density. So some of the interesting points one can observe from this graph is that if you talk about one of the quite famous processor, that is the Pentium 4 processor, a Pentium series, which ends somewhere around in 2005, and after that there is no more Pentium series. And but if you see the clock speed somewhere, it uh, roams around or takes around 2 to 5 gigahertz actually, if you see here. And even in after, let's say 20 till today, let's say even after 15 years, most of the processors are here actually taking it this place actually, even if you take about this quad core or multi-core processor. So the clock frequency is almost stagnated even in last 15 years. So this is the one observation actually. And the reason behind is that if you just move to this another axis, actually on this axis, then we will find that the power density has reached to its limit, that is basically the 100 watt per centimeter square, and which is the power density of the nuclear reactor. So we cannot move beyond this. And we also know actually as a device engineer or electronics engineer, the power is having a direct relation with the frequency. So if we keep on increasing the frequency, the power will increase. As a result, the power density will also increase. So this is the limitation actually. We cannot move, because if we move, go beyond this, then definitely we cannot hold these devices because their power density is too large. They becomes too hot or even very difficult to cool them. So this is the one aspect with the today's computers or today's processors limiting to the speed to 2 to 5 gigahertz. And another aspect, if you look at towards this back to this graph, then we will see the brain somewhere here, and it usually takes around a few hertz, and the power density is very good, just few watts per centimeter square. So, so this is what the main area where lots of research are fascinated to have computing inspired from the human brain because of very low power density, and also it operates just very few hertz. And it has been observed that the human brain with less than of 20 watt of power offers a very good computing capabilities of the order of petaflops mark. Thus, it outperforms the state-of-the-art supercomputers by several order of magnitude in terms of energy efficiency and the volume. So you may be surprised that let's say even for a human brain, finding this, let's say 3 raised to the power 289 may be a challenging, but uh, it is not always to have this such kind of computations. So human brain outperforms in many cases. For example, I will give you a couple of examples like cognition, decision making. So these are the area where this human brain outperforms. So this is the what the main focus or the motivation. And let me just put all these things together. Then the energy efficiency is one of the aspects that I mentioned because of this biological brain in comparison to the state of the art supercomputers. And with just 20 watt of power, it can performs or even it can outperforms with the state of the art supercomputers. And here are the two examples. The example first, let me just show you. I will discuss in detail also this example. The Blue Gene supercomputer that consumes a megawatt of power actually when we simulate a cat's brain activity actually. So megawatt of power, you can imagine, just for a few minutes or few hours, let's say, if we simulate the cat's brain activity, then it consumes megawatt of power, which is quite not feasible actually. And another thing is that the AlphaGo game, a very nice game, basically it is a board game. And for developing this algorithm for this board game AlphaGo, uh, and it is implemented on a supercomputer, and it consumes the energy or the power some of the order of megawatt. So for this small game that human brain can nicely perform actually or nicely play, but if the same game has to be played by the computer and it is the algorithms developed in the deep algorithm developed uh, and implemented on the supercomputer, it consumes a huge power actually, but it can nicely be played with just very amount of energy through human brain. So this is what the main area where the brain-inspired computing is having good potential. And finally, some of the tasks, as I mentioned, that the human brain can outperform, which includes the cognition, control, movement, and decision making. And all these tasks can be rendered simultaneously with just 20 watt of power. So this is what basically the main motivation behind looking towards the alternative computing approaches. So for that, actually, let me just put these two computing approach one to next to each other, and then we will see major differences between these two. And then I will take this architecture also in detail. So this is what the one human computing architecture, uh, a more widely used computing architecture. If I say virtually all the computers today have this architecture in all the computers. So here I have put basically the higher level of abstractions, just showing three blocks, three important blocks, which includes the memory, the CPU, and the IO devices. However, there are plenty of other components, but these are the three important components. So from these components, what we can see actually, or what we observe, that whenever some operation has to be done, the data need to be fetched back and forth, or flipped back and forth, or shuttled back and forth between memory and CPU. And then some of the data may go to the IO devices also. So during this process, the shuttling process or the movement process of the data between CPU, IO, and memory consumes lots of energy, as well as it creates a bottleneck for movement of the data. So it also introduces a latency, or throughput is goes down actually. So to avoid all these things, if you look at the another alternative brain-inspired computing architecture, we know the human brain or brain usually don't have these separate units basically. Even memory and processing goes neck to neck, right? So this is what the one reason. So if we put these two architectures together with some numbers, then we will see the human brain is completely parallel architecture, and it performs computation in an analog domain. The one of the important element or computational element in the human brain is neurons actually. So it is having almost 10 raised to the power 11 neurons, and the processing or the activity takes place just with a very small frequency of a few hertz, that is tens of hertz. And each neuron is connected through a 10 raised to the power, or in other words, sorry, there are 10 or 15 synapses. In other words, each neuron, the single neuron, is connected with almost 10,000 synapses approximately. So highly dense and parallel system, you can see from this picture also. So one neuron is having almost 10,000 connections. So through these synapses, so it carries the information, and also it holds the information while transmitting the information. So this highly parallel and highly connected network provides this facility basically. So, and however, in our traditional computing architecture, if you see there is not enough parallelism, uh, and the density is also not of that level. However, but nowadays you can see we have chips having billions of transistors. So that's why now people are looking with these type of architectures where parallelism and the number of component can be increased significantly. So as I mentioned in the previous slide, there's the Blue Gene supercomputer. So this Blue Gene supercomputer was used to simulate some these mice activity, brain activity for a shorter duration, and it was implemented in the traditional computer, that is the one human computing architecture, which is digital in nature. And the neurons they realize were something 8 into 10 raised to the power 4 neurons, digital neurons. Please keep in mind they are digital neurons. So digital neurons were designed, and then there are digital synapses, so were designed, and all these synapses and neurons operated 1 gigahertz. As a result, it consumes almost 40 kilowatt of power actually. So this is how lots of research, lots of work is going on, how to make these computing architectures more energy efficient. How do we get computations or inferences related to the human brain, because this architecture, this one human computing architecture, is not that efficient. You can see here also. Then there are a couple of recent work actually. The IBM has demonstrated a chip that is called IBM True North. So they developed a chip that is called True North, in which there are 4096 cores they use, and the number of digital neurons they designed was around 1 million, and the number of synapses was 2.5 into 10 to the power 8. And they use this chip, basically True North chip, for making some small inferences or recognizing some object, and the power consumption was significantly low actually. So you can see it is somewhere around 63 milliwatt, which is quite good, but for some limited task actually they demonstrated this. And if we compare these IBM True North chip and a human brain, then we will find there is still a huge gap still persists actually, and lots of research or work can be done in this area. So in continuation to this IBM Truno, let me give you some more details, and those who are interested in this chip design and the working and other aspects, you just Google, you will find out about the detail. And also I think this detail of this chip I have referenced also in the very first. So you can get it, there is no problem. So as I mentioned, the human brain is comprised of these many neurons and these many synapses, and it consumes around 20 watt of power. And the main thing actually in this IBM True North, however, the neurons and all these things are digital in nature, but the information they process is in the form of spikes actually. So you can see the spikes being used rather than the zeros and one continuous that we use in this digital system. They use basically these kind of spikes. So the spikes, all the information processing, decoding, encoding, all these things was done through spikes. And we know that the human brain, most of the activities takes place in the form of spikes. All the information processing, storage and computations, all these things is being done through spikes. So they took this spiking neural network kind of things. So spiking neural network is also one area where lots of work is going on, because it is having a quite good resemblance with the biological neural network. So some of the important parameters I have already mentioned, the number of transistor count. So this chip is having almost 5 billion transistors, and it occupies almost 4.3 centimeter square area. And this IBM True North chip is based on Samsung's 28 nanometer technology process. You may be surprised why they use this Samsung, that I don't know. And the total power it consumes somewhere around 17 milliwatt for making some small computations basically. And if you see, to realize a biological neuron here in this chip, uh, if you see, it requires almost 10 raised to the power 4 transistors. So for one biological neuron, they require or they use almost 10 raised to the power 4 transistors. So you see, if we can have a model with limited number of a model of a biological neuron with less number of transistors, then the efficiency and the computing power can be further improved actually. So just to give you some more details, as I already mentioned, all these things are also summarized here. So in this, they use the digital synapse, which is based on 8 transistor SRAM cell. Also, they use digital neurons and the digital synapse, and these things we have already discussed. So the power consumption for a simple task, that is for object recognition with a very low clock frequency of the few kilohertz, and it was just 30 frames per second, and the power consumption was 70. So this is the initial or very latest demonstration by the IBM for towards this brain inspired computing chip or neuromorphic computing chip. In this same direction, the Liohi from Intel. So this is from Intel, Liohi chip. This is also a architecture which is inspired from the human brain. It is also called the neuromorphic computing chip, Liohi chip. And in this chip, I think I'm just giving you some overview about the different the models or technology, the neurons and synapses. You can see this is based on 14 nanometer technology, and they use these many cores, 128K neurons, 128 million synapses, and the total transistor count is somewhere around 2 billion transistors. And the important thing here, you can see here, they use this LIF model, leaky integrate fire model. LIF model, that is basically a leaky integrate fire. The property, so this model is having a very good resemblance with the biological model because it generates a kind of spikes as being generated by the spikes of the human neurons or biological neurons. So they use this kind of LIF model for for realizing these chip actually. And then you can see here the efficient spike based communication they have used between these, the data encoding and decoding and so on. So this is the second demonstration or second experimental chip from the IBM. Apart from that, just we can move. So now now the question arises: what is basically this neural computations or biological computations or brain inspired computations or neuromorphic computations? There are plenty of terms being used nowadays, actually. So the objective here is that not to, let me just emphasize here, not to reproduce the computing power of the human brain, but to inspire or to just draw some inspirations from the human brain, how the human brain performs the computation. So the similar kind of things we can do through our transistors or through our computers. That is the main idea here is. So here our aim is to develop the engineering level description or a kind of model, and these models can be used for solving the problems or model of the brain system. So most of you may be familiar about this structure actually. So this is very popular model of the perceptron neuron model, most commonly used in ANN, artificial neural network, and it is very the first generation or even it is a second generation model, perceptron model. And in this model, if you see that there is let's say some input vectors or feature vectors are coming, and then they are multiplied by these weights and then summed up and passed through a activation functions, and finally we get some outcome or output. So this process we keep on doing, and we keep on adjusting these weights till we can match or map the input and output relationship, and this process keep on going on. And once it is done or accomplished, the matching between or mapping between these input and output relation establishes, and corresponding to that these weights will be adjusted, and then we can give some any random input, then the system will perfectly recognize those things. So this is what the idea. So you can see here there is very less resemblance or relation with the biological brain, and the same model can be represented through a mathematical model. So you can see the same picture that you see here, it is having its equivalent mathematical model. So developing this mathematical model is very important actually, because these mathematical models are usually implemented in our computers through some different algorithms. So here you can see this is what my input, and these are the weights, let's say. So these are multiplied by the weight and then summed up. It is also called basically the MAC operation, multiply and accumulate. So we are multiplying the weights and the input signal, and then they are accumulated. So the MAC operation is done. Then there is some bias function, some bias is there, not functions, bias, and it is passed through a non-linear function G, non-linear activation function. So there are plenty of these activations functions. So these functions you can choose depending upon your applications, depending upon your application, and there are different type of function. So here in this we are trying to improve, basically we are trying to find out some better models. Those models can be implemented through our integrated circuits or some new devices. So that is the idea overall, and this is how the overall representation, how the things in the human brain takes place. So we usually recognize this through this way actually. All right. So now we have the idea about basically how this brain inspired computing, what are the different models and what we need to do, and also what are the main motivations. So in the same, like let's say, now next part is that I mentioned, so the in-memory computing. So the in-memory computing, before I move to the details in in-memory computing, and then I will show you a couple of examples also based on both. then you can see, let's just look at brief about all these things. Let's say, so the idea here is that, is there any something wrong with the existing computing architectures? So I showed you one architecture, simple one human computing architecture. So is there any something wrong? Actually, we will try to find it out. We know this one human computing architectures is here for several years or several decades, basically several decades. So, but we will still just look at the abstract level, higher level of abstractions, and then how we can provide the energy efficiency, because the existing computing architectures have failed to provide adequate computational and energy efficiency. So adequate computational and energy efficiency in the sense that we have seen last 15 years almost the clock speed is almost stagnated, and still we need some more energy efficiency also. So once when we try to answer these questions, then we can say, okay, we can ready for this in-memory computing. All right. So let me just revisit again that same architecture that I just gave you briefly in the very first slide as a motivation. And here I'm putting basically the two architectures. The one is the one human computing architecture and is the hardware architecture. So these are the two architectures. And if you see, virtually all computers are based on one human computing architecture. So the hardware architecture is not that popular, but just from study point of view, just from okay, there is also one more architecture, so I have put this architecture also here. So now you see both architecture, if you see, there is no big difference. If we can break up in three major building blocks, both the architecture, so they have the common memory, CPU and IO devices. So the problem is again the same, actually, as I mentioned in the beginning also, the movement of the data between these building blocks and movement of the data through long buses, and or also called shuttling of the data, because your CPU, you need data to be processed and then it either sent back to the IO devices or it's sent back to the memory unit. And during this process, actually, if I say almost 70% of the energy is dissipated in this process. And to address this issue, actually, there are different level of memory hierarchies have been introduced, actually. So it is just, I'm showing you three building blocks, but if you see, the CPU is equipped with lots of inbuilt memory. So that is what a different type of memory hierarchy is being introduced. So there are a good amount of memories inbuilt so that the movement of the data can be minimized, actually. And if you just look at some typical processor die, so let's say if I say it is your titanium processor, titanium 132 nanometer, little old processor, let's say, if you just look at, and if you see, almost 80% or even 70% of this die area of this processor is occupied by, almost 70 to 80% of the die area of this processor is occupied by the memory. So there are different level of cache memory, L1, L2, L3, and even the number of transistor count is also dominated by the memory chips. And the reason behind it is so that the frequent movement of the data from CPU to memory can be minimized. That is the main idea, actually. So therefore, lots of memory is being incorporated, and there is just very few building analog or digital blocks actually in this part, let's say, just as a representation. So we can see, so it means that these dies and these processors are not digital chips, they are basically the memory chips. So memory is more crucial, and the reason behind is this, actually. So can we, so the now the thing is that since these digital these computing processors are completely memory chips, so can we perform some kind of computations within the memory, actually? So every time we don't need to send the data to the CPU and then again come back, or can we minimize the shuttling or the movement of the data? That is the idea, actually. So so there are, as I mentioned, there are different type of memory hierarchies being introduced. So there are L1, L2, then secondary memory, tertiary memory, and so on. So just give you the brief about this memory hierarchy and the performance parameters. So this is what the memory pyramid actually. So on the top there is a SRAM register, then there is a DRAM, some secondary memory, and so on. So if we go from top to bottom, actually from top to bottom, let's say, so in this case, let's say here, this graph, if you see, so the area or the the amount of memory is keeps on increasing in the sense that the register files and the SRAM is just few KB, or maybe just SRAM maybe few MB. So these register files are few KB or few MB memory, inbuilt memory, few KB, let's say, or few MB SRAM. But as we move on down, let's say, so this flash memory or hard disk is of the terabyte of the order, TB, we know. So the capacity keeps on increasing as we move from top to bottom. Similarly, if we move from top to bottom, then the speed or the clock speed, let's say if we talk about speed also keeps on reducing actually, or the delay keeps on increasing. So the SRAMs are usually much faster than this memory. Similarly, if we talk about the cost, then the cost keeps on increasing. And the reason is simple, because if I want to have a 1 bit of storage, then the silicon area I need in for SRAM, it is somewhere around let's say 6 transistor. But for DRAM, same 1 bit, we just need a 1 transistor and 1 capacitor that can also be integrated on top of it. So the silicon area required here for 1 bit of information for 60 DRAM is almost 5 to 6 times more than the DRAM. So that's why this is more expensive than this. Similarly, we move on to flash and other memory, then the cost keeps on reducing because they are not that more silicon area hungry, or that's why the technology is not that expensive actually. So the cost keeps on increasing as we move from bottom to top. Another interesting observations, if you see here, which is also a very important factor for deciding this memory hierarchy or choosing a specific type of memory, which includes, one is this endurance. Endurance is basically the number of cycles performed, number of read or write operations performed during the life cycle of a product, let's say. So if we see this NAND flash and these SRAM and DRAM, then the number of cycles here in this flash memory is very small, maybe of the order of 10 raised to the power 5 or 10 or 6, so somewhere around 1 million cycles or read and write operations it can perform. That's why sometime you might have also observed that your pen drive or your flash drive get damaged. Actually, it is not functioning after 1 year or 2 years, and the reason is simple, because its endurance is limited actually. So, but in case of the SRAM and DRAM, the number of cycles can be very large, and it is obviously we need these many operations to be performed during the life cycle of that product, somewhere 10 or 15 and plus. And there we know that the number of read and write operations performed during the processing and this SRAM is huge, so we need this type of high endurance memory also. But another aspect, if you look at on this axis, the delay actually involved for read and write program. So this flash memory is slow. So if you are going to integrate this flash memory as a let's say cache memory, then obviously there are two reasons it cannot work. One is the endurance, another is they are very slow. So your performance of processor is completely grilled off. So that's why they only fit as a secondary class memory or solid state memory here. So they cannot be used as a cache memory. So these SRAM, and they are having a very low time for read and write cycle, so of the order of few nanoseconds or even the fraction of nanoseconds. So this is how the memory hierarchy being used to bridge the gap between the processors and the memory. So this memory hierarchy is very crucial. If you see here, as I mentioned, lots of data is moving from here and there. So a different type of memory hierarchy is being introduced in between. Even some of the type of memory is also incorporated in the chip itself or in the processor die itself. to minimize this movement. And also to this another graph actually this shows how the gap and it is also called basically sometimes memory wall, how the gap between the performance of a DRAM and the performance of a CPU keeps on increasing with time. So the performance of the DRAM increases almost 9% per year, and that is it doubles almost 10 years. But at the same time, if you look at the performance of a processor is almost 60% per year, and it doubles in just 1.5 years, that is 18 months. So the performance or the scaling of these digital chips, it is all about basically the scaling, right? So the scaling of digital chips is much easier, we can say, or convenient as compared to scaling the DRAM. So that's why there is a gap in the performance. However, this data is slightly old, you can see, but still if you extrapolate this, then you may still find some gap maybe still exist actually. So this is also called the memory wall or some memory gap. And this gap again can be minimized by incorporating the cache memory, so that the processor need not to wait for a long time because this performance is quite slow. So we incorporated cache memory which is having quite good performance, or the performance matching with the processors, if you see here. So that is the idea. All right, so with this now we have set the kind of stage, we can say, for this talk. One is why do we need this in-memory computing, and why there is a need of brain-inspired computing. So let me take you to the some real term examples, or uh, where we can use this architecture actually, or how it works. So a detailed picture of how traditional computing versus in-memory computing works. So the traditional computing, if you see, we have a conventional memory, then we have a processing unit, as I am emphasizing from the very beginning of this talk. So whenever some operations has to be done, the data need to be fetched basically from this memory to this processing unit, which contains control unit, cache, arithmetic logic unit, and then the data comes over here, and this ALU performs some operation or some function f on this data D, and then it's sent back to this memory. So and the result is again sent back to memory, or it may be sent back to some IO devices also. So this is one case. This is what the traditional computing. But if you see some alternative computing, as I mentioned, let's say in-memory computing. So what if I bring this small computing capability to the memory itself? So this small computing like this arithmetic and logic units, or in other words, if I can do some basic computations within this memory fabric, like AND operation, or some OR operations, or some kind of, let's say, MAC operation, which is more commonly or widely used in AI or ML application, so that we can design a new architecture which is good for AI and ML application. Also, there are plenty of new these application specific architectures are popping up, right? So the idea here is if we can we bring this little computing power to this. However, it is not supposed, I mean, it is not emphasized, or it is not supposed that we are completely getting rid of this unit actually. So even in this in computing approach, we also have this processing unit, but the only thing is that we are bringing some small computing capability here itself. So how do we accomplish this actually? And that is the objective, that is what the in-memory computing all about. So the question arises, how do we do this processing within the memory? All right. So for more details, you can look at to this paper, this from this Nature Nanotechnology at the bottom. Okay, so as already I have mentioned this example, we have already seen, but here I'm giving you one example of one live example, let's say in terms of energy efficiency. So I have explained all these two models. So let's assume that these weights, these are the weights, let's say. So the weights, there are two possibilities. One, this is again to basically how this operations or in-memory computing is important actually, again to emphasize why and how this in-memory computing is important. So let's say these weights are there are two ways. One is the weights are locally stored, and two, the weights are fetched from main memory, fetched from memory. So if I'm doing these computations in two, let's say in two ways, one is the weights are locally stored, and second, they are fetched from the memory, then the amount of energy, so let's say the E1 in the one case is somewhere around 3.2 picojoule just for one MAC operation. And in the second case, if the weights have to be fetched from main memory or secondary memory, then the amount of energy it requires 640 picojoules. So now you can see for the same operation, now you can see the energy, where your energy is going. It is very obvious that energy is mainly going for fetching the data. So if I can have these weights locally, one thing, or in other words, if I can do computations locally, then, or locally in the sense, then let's say my weight is stored in the memory and there itself I can perform this MAC operation, then I can save lots of amount of energy, almost 200 times, 200x the energy if you see here. So this is what basically 200x, or yeah, somewhere around. So significant amount of energy saving we can get actually. So how do we do this thing? That is the task. So here is what a simple example we can do this object. We can achieve this thing actually. All right. So how do we do this thing? So you have seen this is a very simple MAC operation, that is the multiply and accumulate, and this can be done through various ways. So the device and the circuits that we can exploit, there are variety of circuits and devices you can exploit. So here is one simple example. So let's say we have a kind of a small part of a crossbar. So in this crossbar, these are, let's say, your rows, and here is just one column. And at the intersection, we have connected one device which is having a transconductance G1, another device which is having a transconductance G2. And the amount of current flowing through this is given by this I1 or I2. So this is can be V1 G1 plus V2 G2. And now if I generalize this expression, so your generalized expression will be something like VG. So here V is nothing but the input vector and the G is your weights actually. So this is what exactly the same that MAC operation I was telling you in the previous example. This is equivalent to this. So we can extend the same concept actually, and we can realize this operation even without using any kind of arithmetic logic unit. Just with a simple circuitry we can realize this, and it has huge power to for certain applications, as I mentioned. So you can train this network, you can build a crossbar network with certain device. Maybe you can use memory store, or you can use some patience memory or some other memory element or some other element, and you just train this, you can get this kind of operation. And a more sophisticated way, you can go this way also. So this is again the same thing basically if you see. So we have a supply voltage connected here, and this is basically gated through this transistor. So if this transistor is on, only this part will be active, otherwise this will not be active. So if this is on, then you will get the sum of all these currents multiplied by these weights. Let's say these are the weights. So this into this, x0 times w, x1 times this, and so on. And this can only be there if this current I, j, is only when your xj will be there. Otherwise, this is 0. So this thing can be represented through this mathematical expression as follows. So the ij is equal to the sum of all the currents for xj, xi, and wji. So you can see from here, if this becomes 0, so this entire stuff becomes 0. So this is a generalized way of getting this multiply and accumulate operation in a analog domain actually. So this is what we are doing, basically the analog vector matrix operation. in a better way, actually, let's say this, if I extend the same thing for certain applications or certain operations. So let's say if I have some data point, this 0, 1, 3, 2, this is what my input, and it is transposed basically, and then it has to be multiplied with another data, that is 3, 6, 2, 1, matrix multiplications, and then the result I will get 14. So without any arithmetic logical operations, we can accomplish the same task through a simple crossbar architecture like this, through this simple crossbar architecture. Over here, so as I mentioned, that these weights and these feature inputs, we don't need to fetch them from the memory, but they can be represented through some transconductance of these memoristors or some memory elements. So this structure is represented in this form actually, if you see. So the let's say this, your input is represented in the form of 2-bit. So 0 is corresponding to 0 0, 1 is 0 1, 3 is 1 1, 2 is 1 0. And similarly, the data is represented again in the 3-bit form. So it start from MSB to LSB. So 0 1 1, that is corresponding to 3, 1 1 0 corresponding to 6, 2, and 1. And finally, by doing some small analog conversion or shifting the data, we will get the result 14, and without any kind of arithmetic logic unit or any kind of processing capability. All can be done in just analog domain, or even in just a one clock cycle, or just in one way we can do it. All these things actually, you will get this analog product actually in one go. So this is what the main advantage of doing the computations in analog domain rather than the traditional, because we can avoid a significant settling of the data from memory to the processing unit and vice versa. All right. So in this direction, actually, there are lots of work in the recent past, if I say, has been done, specifically in the in-memory computing or this. So this work just put in the form, let's say, this NVM, that is the work based on non-volatile memories, SRAM, static random access memory, and the DRAM. So if you are interested, you can, I will share this presentation. You can also take these things and just find it out, the complete paper about these different demonstrations or the architectures people have already done in the last 4 or 5 years. And there are more work in the last and in the previous 2 more years, let's say, because it is in 2009 up to 2019, sorry. So in this talk, I'm going to show you two simple computation approaches through SRAM and DRAM actually, so that you can realize and you can understand, and even you can simulate also in your SPICE or any other tool. So let me take you to the to real world example, how we can do the in-memory computing. And before that, let me just give you a brief idea about the basic memory elements, so that you can follow the discussion easily actually. And so there are different basic memory elements for in-memory computing, and these elements are divided on the based of the charge, or on based of the form in which the information is stored. So the charge based memory and the resistance based memory. So in the charge based memory, the information is stored in the form of charge in these nodes, at these nodes actually. So this is what the SRAM cell, a typical S6 transistor SRAM cell, in which you can see there are 6 transistors, these 2 inverters are having 4 transistors, then these 2 excess transistors. And these nodes holds the information in the complementary domain. So let's say this is 1 and this is 0, and then there are 2 lines, one is called the word lines and another is, sorry, bit lines, and another is the word lines. So this is what the static random access memory, more widely and more commonly used form of cache memory actually this. Then there is a DRAM. You can see the DRAM, as I mentioned, the DRAM just require one transistor here, and that is also a access transistor AT, and then there are dedicated capacitor for holding this information or charge. So the absence or the presence of the charge is indicated whether there is a information or there is no information, or that is corresponding to logic 1 or logic 0. Then there is another class of memory where the information is also stored in the form of flash. So before moving to this class flash, let me just give you some more idea on these two memories. These both memories are non-volatile in nature actually. Volatile in nature. Volatile in the nature in the sense that if the power is there, then information is there. Other, if no power, information is lost. But this flash memory, you can see, this is a non-volatile memory. Even you remove the power, your information is retained there actually. So that's why you may have observed that in the flash memory, your information is retained even you carry without powering it up. And this is made of a single transistor, a special type of transistor usually used, that is called the floating gate MOS, sometimes also called FAMOS, floating gate MOS transistor. So this transistor, if you see it, this or this gate here, it does in between. So this is not connected to the anywhere actually or external world. So that's why it is called floating gate actually. And it works on a principle that when we apply certain bias across this line and this line, and then this is on and off, this word line, this is bit line, then the charge trapping and detrapping takes place actually. Charge trapping or detrapping takes place. In the sense when the charge still takes place or charge is trapped, then the VTH of this transistor or this device is shifted basically, and it remains there actually. So there is a change in VTH, and that represents basically the kind of operation, let's say kind of information. It is corresponding to write 1 or writing 0 actually. And then the detrapping, whatever charge is basically stored, then it can be flushed out, or this is what we can say the erase operation. So the VTH of this device is returned back to its original states, so it can referred as some state 1 or 0. So this is how the information is represented in this flash memory. Then there is another set of memory basically that is called the phase change memory or resistance change memory. So in this resistance based memory, the information is stored or information is represented in the form of change in resistance. So we know that the any device which can be having high resistance state or low resistance state. So this high resistance state can be thought of for having, let's say 1, and this can be 0 or vice versa. It is just depending upon your architecture or your convention. So but these two states are highly distinguishable, and they can be represented through the logic 1 and 0. So just by applying the bias, we can set or reset these states from high resistance state to low resistance state or vice versa, and that represents the information in the form of logic 1 and 0. So there are variety of elements and the circuits that can be used for resistance change memory. So let me move to the design in memory computing building blocks. So like for example, doing AND operation through SRAM actually. So how the SRAM can be used for performing the AND operation or operation, or maybe some other operations that you can think actually. If you just do little thought process, then you may be able to do some XOR or some other operations. So here I will show you how these memory elements, they are mainly designed and mainly or they are dedicated only for storage information, but they can also be used for performing these operations. And once we can perform these operations within the memory there itself, then we can use some other useful operations also, like MAC operation. So before, so let me give you a little idea about the working of this SRAM actually. So those who are not familiar with this, they can follow this talk very closely. So that's why I kept this slide blank. So let me just draw the memory building block circuit diagram. So you see there is a one inverter, and then there is another inverter, and these two inverters are connected back to back, and it forms the basic building block of information storage, and this is also called a kind of latch. So this node if both these inverters are powered up, then these nodes will take either 1, 0 or vice versa. So it depends basically whether this node will be 1 or 0 or this node will be 0 or 1. It depends basically due to some manufacturing variation. So if the one transistor or one inverter is weaker and then is stronger, then one node will go to 1, another node will go to 0. And certainly they will reach to this stable state if both cannot be 1, 1 and 0, 0. So it becomes stable. And then this is what the information is represented within this latch. And then for reading or writing this information, we need some gateways actually. So we have two access transistors, as their name implies, access. So they allow the access of the informations to the external world, and they're connected through a line that is called word line. So this is what my word line. And then there is a bit lines. So these are the bit lines, bit line or bit line bar. So now you can see there are 6 transistors. So this is what my 81, here it is what 82, and the 4 transistors are here. So total 6 transistors are here. So just give you idea about how the read and write operations takes place quickly. So for example, if I want to write, let's say first let me talk about write operations, and then read, and then hold. These are the 3 commonly used operations in a memory, any memory element you take. So for writing, basically what we do, we dump or we put the data on these data lines in the complementary fashion. So these the bit lines are also called the data lines. So we need to put the data, let's say if my data is 1, then this data has to be put on complementary fashion. So let's say 1 will go here and the 0 will go here. So put the data, first step we can say put data on data lines, first thing. Second step, enable word line. So we need to turn on the word line. So word line is equal to 1. So when this word line is 1, it means these transistors are on. These transistors are on. So now you can see this is 0 and this is 1. So obviously there is a flow of current this way. And this is 0 and this is 1. Sorry, just a minute. So there is a flow of current other way around actually, this way, because this is at 1 and this is 0. So there is a flow of current this way, and there is a flow of current this way actually. So you can see this bit line is trying to make this 0 to 1. All right. This bit line is trying to make this 0 to 1, and this bit line is trying to make this 1 to 0. So this is what the pulling up and down is taking place, and this operations may be this process is maybe left for some few fraction of nanoseconds, and we can accomplish successfully the write operation. So this node becomes 0 and this node becomes 1, and we can write it successfully. And till then, this word line has to be enabled. If we pull this down word line down, then this process will not be complete, and we may be having a write failure actually. So this is how the write operations can take place. Second, if I talk about the read operation, let me change the color of this pen just to show you read operation. So for the read operation, what we do, so very first thing, we precharge these bit lines actually. Precharge bit lines. So precharging bit lines in the sense that we can connect them to some voltage level, that is, let's say VDD. This is connected to VDD, this is connected to VDD. Please keep in mind, these are just precharged. They are not tied to VDD. They are not tied or connected permanently to VDD. They are just precharged, and then they are left open actually, or floating. So they are precharged to VDD. And then second thing is enabling the word line. Enable word line. So the word line is enabled. So when this word line is enabled, so let's say if this is now I assume that the information is still 1 here, and this is 0. Information is 0. I'm doing on this. Okay, we can assume this is the data is there. So when this is VDD and this is also VDD, so you can see there is a flow of current this way, but there is no flow of current either way, because this node and this node both are at the same potential, so there is no flow of current. And if I draw the timing diagram under the read operation, so this is what my bit line, they are pre-charged to VDD. So both bit line and bit line are here, pre-charged to VDD, let's say. This is corresponding to 0. And then after that, I turn on this word line. It's a 0 to VDD. Sorry, let me draw bottom one. And then after that, sometime I activated or enabled this word line. So this is VDD here, 0 and VDD. Now what will happen, that one of the bit line will remain high, but another bit line after this point will start discharging, because you can see there is a flow of current. So this bit line, let's say bit line bar, will discharge. So this is what my bit line, and this is what your bit line bar here is. So there is a difference in this potential, and this difference in this potential of the bit and bit line is sensed by the sense amplifier at the bottom. So there is a sense amplifier is connected at the bottom, and the sense amplifier will sense this in difference. So it will give you at the output 1 or 0, because sometime your bit line will discharge, and another time your bit line bar will discharge actually. So this is how the read operations takes place. For hold operation, it is very simple. You just need to make this word line equal to 0. So once this word line becomes 0, both these transistors are out of business, and your cell will remain isolated, or it is in hold state. It will hold the information. So this is how basically all about the SRAM. And the DRAM is also very simple. So I think, let me just take you a quick operation of the DRAM. Sorry. So here is what access transistor, which is connected through this. This is bit line, this is word line, and then there is a dedicated capacitor. Sometimes this node is connected to ground, but usually this node is not connected to ground. It is always having some supply voltage actually, and the reason is it increases the retention time actually, so that every time we don't need to refresh this this capacitor to having the information. And then there is an access transistor, AT, let's say, and this is word line. So when this word line is high or low, then this capacitor can be connected to this bit line, and this bit line can sense the absence or presence of the charge on this capacitor, and this absence or presence of the charge can be thought of information 1 or 0, or logic 1 or 0, or vice versa. And similarly, for writing operation, we can write the data, or we can dump the data on this bit line, and this data can be transferred if the data to this capacitor. So if this is high, then this capacitor will charge, and if it is 0, then this capacitor will empty, let's say. So this is how the writing can take place. Just in a very crude way, I'm just explaining you, because objective of this talk is to have how we can use these elements for computation purpose. All right, so moving to this main objective. So here I'm going to show you how we can perform this AND operation or NOR operation through these memory element. So the very few things that we need in mind actually. So one is, so let's say if I want to design a 2-input AND gate. For 2-input AND gate, I need to select one column and 2 rows from SRAM array, from a SRAM array. So here I have chosen one column. You can see this is one column here all the way, and there are 2 rows actually. So the row 1 and the row 2. So if you want to design a, let's say, 3-input AND gate, then what you need to do, you need to select 3 rows actually from the same column. And if you want to design a 4-input AND gate, then you choose 4 rows actually, and all these 4 rows should be activated simultaneously. But in traditional memory operation, we only activate one row at a time. So that is the difference in their operations. So when you are using some memory as for computation purpose, so you can divide it into, okay, now this is the computation mode, and it is a memory mode, so that appropriate circuitry can be designed and appropriate control signals can be designed, and they should take care of all these operations in a proper way. All right, so let's take this operation. So as I mentioned, for doing all these read and write operations, so how do we keep this bit line and bit line bar and word line? Now you have some idea. So let's assume that the data, that is the operand, is here A and B. So we want to do the ending of these A and B. So initially if A is 0, let's say B is 0 and A is also 0. Let's say this is the node that represents this A and B or operands. So when both these nodes are 0, 0, and obviously this node are going to be 1, 1, because the information stored is complementary in nature. And then the bit line is also pre-charged. So let me just draw its timing diagram also in parallel to have for a better understanding. So this is what my bit line. And then I activated this word line after some time, or enabled the word line. So this is what the word line. So when this word line is enabled and the bit line is VDD, so what will happen? These access transistor will allow the flow of current this way. And then this bit line is also connected to a difference amplifier, or this is also called the sense amplifier. In another term of this, or terminal is connected to a reference voltage. So it will basically kind of comparator. So this voltage on this bit line will be compared with the reference voltage, and corresponding it will produce an output that is the AND A and B. That will be the ending operation. So now you can see here, when this bit line is high and this word line is also enabled, then this bit line will discharge. The bit line will be discharged. So here the bit line will discharge this way, something like this. So when this bit line is discharged, and if, let's say, if the reference voltage is here, somewhere here, this is what my V reference. So this sense amplifier will compare this voltage, these two voltages. This is the bit line voltage and this is the reference voltage. So you can see the bit line voltage is here. So VBL is less than V reference. As a result, it will produce the output 0. And this is what you can see here also. For 0, 0, you can see the voltage, the output is less than this reference voltage. So it is corresponding to 0. Hope it is making sense. Now let's assume the another worst case. So I'm changing the color so better clarity. Let's say, so assume that now in the second part, where is my pen? Yeah. So if this is 1, let's say this node is 1 now, this is also 1, and I pre-charge this bit line to VDD, and I turn on this word line here, let's say after some delay. So this is what my bit line and this is what my word. And now you can see these excess transistors are off in this case, because both are at the same potential. This node and this node, this node and this node, both are at the same potential. It means that the potential on the bit line may be having a slight droop. And here it is what, let's say, assume this is what the reference voltage, V reference. So now you can see now the bit line voltage is higher. So in this case, my VBL is greater than V reference. Hence, the output voltage here, it is going to be 1. The sense amplifier will give me 1. It is very clear. So this is corresponding to this case actually here. And here you can see the voltage is higher than the reference voltage. So this is what my reference voltage and this is what my bit line voltage. So I will get 1. So now you understand, when 0, 0 is there, then I will get 0, and when 1, 1 is there, I will get 1. And for better understanding, I can rewrite here. So in this case, actually, you can see both excess transistors are on. In this case, off, both off. But what about these two cases, 0 and 1, 1, 0? Obviously, in this case, now you can have understanding one of the transistor is on and one of access transistor is off. So one on and one is off. One off, on and off, on and off, both on and off. This. So the voltage level here is slightly higher than this and lower than this, you can see. But still, this voltage is lower than this reference voltage. As a result, here it is also corresponding to 0 and 0. So now you can see this is the truth table or the representation of a AND operations, and you can get a AND operation. And the same you can extend for 3 input or more input AND gate. There is no issue. And this is what you can accomplish a AND operation. Similarly, you can try this for NOR operation, and I'm just giving you the idea how you can do this, how you can understand this, and moving to the next part. So for this, here we have considered the bit line. So this part actually is considered, because this sense amplifier will give you the NOR operation. This sense amplifier will give you the NOR operation. Now you can do the same analysis, same understanding for this terminal actually, or for this node actually. Here now your operands are here. Now your operands are here. So when A0, so A0 is a complement. So let's say this is corresponding to 0. So 0, it becomes 1, and here it is also 0, so it becomes 1. So when they are 1, 1 actually, obviously there is no flow of current. No flow of current. And that's why corresponding to this, the voltage is higher than the reference voltage, and we will get 1. And for the rest, we will get 0, 0. So this is what corresponding to NOR operation, and rest things are as it is. So this is about NOR operations, and for more details you can also refer this paper at the bottom. All right, so I'm just going to show you how the same concept can also be extended for DRAM actually. How the same operation can also be extended for DRAM, or how, in other words, how we can use this DRAM for NAND and OR operations. So again, some basic logistics, let's say. So for if you want to design a 2 input AND gate, 2 input AND gate, let's say, then what we need one column and 3 rows actually. So here basically, if you want to design a n input gate, then you need n plus 1 rows actually. That is the little difference than the SRAM design. And it goes as follows. So here we have these 3 DRAM cells, let's say CA, CB, CB are the internal capacitor of each cell, and these are the word lines. So we have chosen 3 word lines for 2 input AND gate. Let's say 0, 1, 2. And this capacitor CA, CB, we select, they are the internal capacitor where information is stored, and the voltage VA, VB are the voltage at these capacitors. And this bit line is connected to the one of the terminal of this differential amplifier, and another terminal is connected to a reference voltage. So depending upon this voltage difference, this sense amplifier will give you either 0 or 1, or it is simply a comparator that will compare these two and will give you the output voltage V will. And that is basically the either it is going to be a OR operation or it is going to be a AND operation. We can infer like this. All right. So this we can go through and we can understand in the same way. So let's say if I assume that my input is 0, 0 or operands are 0, 0, it means that the capacitor CA is completely empty, it is not having charge. This is also not having charge. And here V select is also 0. So it means all the capacitors are empty and they are completely discharged. And now if I pre-charge this bit line, so if I pre-charge this bit line, So this is what 0 and VDD. Let's say we are precharging to VDD. So bit line is precharged, and then all the word lines are also enabled. After some time, let's say this word line is also enabled. So this is what my bit line. This is word line. Now, if you see, when this word line is enabled, so all these excess transistors are turned on. So there is a flow of current this way, or the capacitor will charge this way. Because these capacitors are completely empty and this bit line is already having a charge VDD, so this bit line will discharge actually this way, completely like this, something like this. So this is bit line. So the bit line will completely discharge. So here you can see the VBL is less than V reference, so we will get 0. This case, the difference amplifier will give me 0. So this is what even you won't get any charge over here. So this is corresponding to 0. Hope it is very clear. Now let's say I'm moving to the another stage, that is basically this extreme another 1 case, and for that I'm just changing the color. So let's say in this color black, or not black. Just a minute. See how this works. This is also not good. So let's say the 1 case here. So 1 in the sense, let's say this is 1. So this capacitor is charged. This is also 1. So this capacitor is also charged, but this is 0. Let's say this is again, because here we have chosen 0. So now in this case, in the second case, when the data is 1, 1, then you see, since this potential and this potential both are at the same potential, so there is no flow of current at all. Similarly here, there is no current flow. So if there is no current flow, then only path exists, only this one. So with this path, the bit line will discharge, but the rate of discharge may be slow, and it is still higher than the reference voltage. So in this case also, my VBL is greater than V reference. As a result, I will get 1. So this is, you can see from here, the voltage here on this line VBL is higher than this reference voltage. So this is the reference voltage, so it is higher. So we will get here 1. And for the rest, basically, now you can see either there existed one more path. So let's say in case of 0, 1 or 1, 0. So one of the 1, 0. So it means that there are two paths exist, this path and this path. So the line will discharge faster, this bit line, and it may be slightly lower than the reference voltage, this case, or in this case also. So what we will get? We will get here 0, 0. So this is the realization of, sorry, of AND operation using DRAM, and I have already shown with SRAM. And the same you can try for this OR operations. The only difference is this: we have to make V select is not equal to 0. So here, if I say there is some voltage, I put some voltage over here, or the V select is having some charge here, let's say. If V select is having some charge here, then obviously if I add only, because you see the expression for the VBL is VA plus VB plus V select. So earlier V select was 0, this part was 0. Now this is having some delta voltage, let's say some voltage is there. So if this voltage is, let's say, some small voltage, so if I add a small voltage in all these, so now you can see here, so the same timing diagram or same chart can be translated into a OR operation through this. So this is corresponding to 0, and these rest are corresponding to 1, 1, 1. This is what exactly you are getting: 0, 1, 1 1. So this is how we can realize the OR operation. So moving to the next, I'm just skipping. So there is another memory element basically, that is the 8T SRAM.
Sir,
Yeah, I think this is there. Yeah, right.
yeah. Okay, so how long will you take?
Yeah, I'm winding up in 2 minutes.
Okay, that will be great.
Yeah. So this what. So this is another type of. I mean, more commonly or widely used SRAM, that is 8T SRAM. So only idea here is that it is having the traditional 6 transistor, and there is 2 more transistor, and these 2 extra transistors allow basically to decoupling of the read and write operation, and facilitate a better in-memory computing. For more details, you can refer this paper. Actually, this bottom I have referred. And then in the same paper, they have explained how the same ITSRAM cell can be used for performing these different operations. And I'm sure once you have understood the operation of these complicated SRAM or DRAM, then it is quite easy to follow these slides and these operations here actually also. So just quickly, let me give you, so this is what your 60 cell, which holds the operand. So assume that this operand is having 1 or 0, let's say, and here is a read word line, this is the bit line. So you can see if this is 1, so this transistor is on, this is 0, so this transistor is off. So this transistor is off means there is no path for current to flow, but there is a path for current to flow. So this bit line will discharge, and accordingly you will get, you can see here, the bit line discharging is taking place in different cases, and they can be used for realizing these different operations. So this is a complete architecture, so I'm just skipping. Basically, the only idea here is that the same SRAM array can be used for both the purpose. So you can have, a only thing is that you need to have a separate circuitry. For example, this is what for classify mode, and this is for SRAM mode. However, this SRAM array is same. If you see, this entire SRAM array is same. Only additional control circuitry we need that will tell this structure that okay, now it is going to be used as a classify mode, or it is can be used as a in-memory computing mode, or it is going to be used as a conventional SRAM memory in detail. So this is what another architecture that we have recently proposed. For details, you can also go through this paper and all about those things. So I can just summarize basically. So we have talked about different architectures that is like for von Neumann computing architecture and Harvard architectures, their drawbacks and limitations. And the major drawbacks and limitations is the huge movement of the data basically, and that is the main bottleneck or memory wall. And the in-memory computing provides basically energy efficient MAC operations that you can that I have showed you. So these MAC operations can be exploited through different type of memories within the memory fabric. And we also talk about the basic memory elements and how they can be used for performing these Boolean expressions. So with that, I would like to close. Thank you all for listening me, and hope you enjoyed. If you have any query, feel free to write to me.
Yeah,
All right, sir, over to you.
Participants, you can write your queries in Q&A section. So, sir, you can see Q&A section.
Yo, just let me see. Yes. Sir, good morning, sir. Just charge-based memory or resistance-based memory, which is more useful for computer? So all memories are useful for computer. Actually, it depends upon their. I have shown you basically the memory hierarchy. So each memory element is having a specific space. You cannot say only the charge-based memory is better or the resistance-based memory. So these memories having a specific location or space in the computer architecture. So depending, and it can be decided on the basis of cost, performance, and the silicon area it requires. So this is the thing actually. Sir, good morning, sir. Please provide some knowledge about non-silicon memories. So non-silicon memories, could you please elaborate, Guru Purneet? Corsi, what do you mean by this non-silicon? I'm not able to follow this. What is the non-silicon memory you are saying? How can we distinguish that the brain computing neurons are digital, and how can we comment on it actually? So the brain computing, so you see, we want to design, let's say, the brain inspired computing architecture, uh, and all our architectures are digital in nature. So obviously these functionality, the neuronal functionality, we have to implement through digital building blocks actually. So there are, I mean, different models. So where they use our traditional digital building blocks for realizing those neurons actually, developing the models. And recently some analog models are also there, that is called the LIF neuron model, leaky integrate fire neuron model. So depending upon the basically the architectures, as I mentioned in the IBM's True North, they use the digital neurons, and also they use the digital synapse. But at the same time, if you go to the Leohi chip, in which they use basically the LIF neuron, it is not a completely digital, it is a analog or a neuron LIF, and that support the spiking neural network also, like other material used in memory. Yeah, so materials used in memories are quite different actually. uh, there are I mean materials, so you can classify the memories on the basis of different materials, like organic, or I don't, I mean no idea actually, honestly, what you're referring about this non-silicon memory. And how do we see the growing use of open source memory design tool VLSI? Yes, there are some open tools available. Even lots of work is going on making things more democratic so that everybody can use. So there are so many tools are coming up in open domain for SOC design and VLSI circuit designs. So this is fine. So thank you.
Okay, so participants, if you have many questions, then
So
please.
which transistor technology node type device is currently used these memories for computations based circuits? If you talk about the latest state of the technology, then the Intel is planning to, or even demonstrated the technology based on 2 nanometer latest, absolutely. But most of the memory or these are still 14 nanometer, or even somewhere around more popular or most commercially used basically. So thank you, madam. Thank
Thank
you,
you.
sir.
Thank you very much for accepting our request to deliver a talk and sharing your research experience with all of us. Thank you very much, sir. And now I request